Hey guys, welcome back to AP Physics C with Whiteley. We're going to be doing chapter 2.6 today, which discusses how to find velocity and position by integration. So over the course of the past couple of lessons, we've mainly learned that velocity is equal to the derivative of position with respect to time, and that acceleration equals the derivative of velocity with respect to time. So with that, we were able to take some function of position time, okay, r of t, which also sometimes in the book is notated x of t if we're looking at just one dimension. And whatever function was given there, say for example 3t squared, we could take the derivative of that function with respect to t to get velocity, 6t. And then if we took the derivative again, we would get the acceleration. Okay, so we did all that simply with derivatives. Now, naturally, this means that you could go backwards. You could start at acceleration and go from acceleration to velocity and from velocity to position. And in order to do that, you would have to use the inverse of a derivative. And the inverse of a derivative is, of course, the integral of your function with respect to time. And sometimes if you're looking for like an actual value, that's going to be a definite integral with bounds there. If you're looking for a function, it would be an indefinite integral. Just depends on your situation, what your question's asking you for. So we're going to be looking today at all of the details on how to do that. It is not quite as simple as one might think. There are a few subtleties that we're going to discuss, but in general, this is going to be somewhat of a shorter lesson because it's fairly intuitive. All right, so in order to do this, we're going to do a quick little derivation, and the derivation is actually going to come from a graph, okay? So when we're doing these integrations, we're going to be starting with acceleration, okay? Last time we went from position, then we found velocity, and then we could find acceleration. This time around, we're going backwards. We're going to go acceleration to velocity, and velocity to position. So we're going to start with a graph of acceleration. Now, the power of calculus is that I can choose any graph for my acceleration. Used to, when we did all the kinematics equations, you had to have something with constant acceleration. Okay, the acceleration had to be a number, not a function. That is no longer true, and that is why this calculus-based physics is so powerful. You can have all sorts of motion now that were previously off limits because your acceleration can change. And that applies to all sorts of stuff. One of those things is spring motion, which you're going to be doing in a lab. A spring has varying acceleration on a load, and we'll see that in lab. I'm not going to go into the details here. But you could have some function for acceleration. I'm going to choose one that looks like this, okay? So that's my acceleration function. We're going to make this only go in the x direction because we're only doing 1D motion right now. And then this is going to be my time. So my acceleration here starts off at a positive value and becomes larger and larger in magnitude. I'm still in, or on the positive side, so still in the positive direction. Now, way back in calculus, you did some fun things called Riemann sums. Okay, we're not going to do Riemann sums here, but we are going to draw from the idea. So Riemann sums took your graph and split it into sections, okay? And if you wanted to find the integral of something, you were finding the area under the curve. That's what the integral does. Integral equals area under the curve. So you're able to approximate that with Riemann sums. There were right sums, there were left sums, there were trapezoidal sums, there were midpoint sums, all sorts of the sums. But the basic idea was that you were going to split your graph into all of these different sections, and then you could figure out the area of each individual section, add it all up, and that would approximately be the area under your curve. And then eventually you should have taken the limit as the thickness of these approaches 0. That's terrible squiggly. But as the thickness approaches 0, if you take that limit, then your Riemann sum ends up being exactly the value for your integral, which is really cool. Well, let's take that really quickly and apply it to this graph here. So if we take one of these sections to be the Riemann sum, okay, we're just going to do like we'll call it a midpoint sum, okay, not really super important. But if we do a midpoint sum, that means I'm going to take the area of this rectangle right here. I'm going to make it a different color. This rectangle right here, I would find the area of. And to find the area, I need to know that midpoint, which is some acceleration, okay? It's the acceleration value at that point, whatever that is. And I'd multiply it by the delta t. Acceleration times delta t. Now, if you think back to your kinematics equations, we are approximating this as a constant acceleration just for that rectangle. You should remember your acceleration equation is acceleration equals change in velocity over time. And you can easily rearrange that to say delta t times acceleration equals change in velocity. So this term that we just created is the same as this multiplication, or the area of that rectangle. So each little area here is a change in velocity. So if you sum all of those up, you take all of these areas and add them up, you're going to get your overarching total change in velocity. So the area under the curve for an acceleration graph ends up being your total change in velocity. I'm going to write that down. Area under curve equals change in velocity. So now we're going to be done with the idea of Riemann sums, and we're just going to move straight on to integration. I'm going to assume y'all know the link with that by now. But integration, symbols like that, that finds the area under the curve. That's the goal. Finds the area under the curve. And we just figured out the area under the curve of the acceleration graph is velocity. So you can take the integral of an acceleration function and it will give you velocity. But there is a little bit of a catch, okay? And I'm going to write out how this goes. So we said integral of an acceleration function equals a velocity function. But here is the deal. Whenever you do an indefinite integral in calculus, that means there are not an upper and lower bound. There is something you have to tack on to the end of your answer, okay? And that is a lovely plus c. That c is called the constant of integration. Okay, and the reason that you have to add on that plus c is because every time you take a derivative, you lose some information. You lose the constant term. It goes away. So when you come back from doing an integration, you have to add on that constant. And that constant, you should know, could be any number. Okay? But in physics, that constant actually has a physical meaning. It's not just a mathematical technicality. It has an actual meaning. This c is always going to represent your initial value. Okay? So if the area under the curve only tells us how much the velocity changes, in order to figure out what your actual velocity is after that change, you have to know the initial. So what this is going to mean is that to get your velocity function, v of t, you're going to have to do the integral of the acceleration function, and then you're going to have to add on a v naught, okay? You're going to have to add on this initial value. So that's the initial velocity. So this same deal is going to apply to a velocity time graph, okay? If we do a velocity time graph, we'll make it look like this again. And you do those nice, beautiful Riemann sums that we love so dearly. I actually really do like Riemann sums. I think they're fun. If we do the Riemann sum there with an average velocity, okay, we'll get the area of that rectangle is velocity times time. Okay, I'm going to rewrite that so that it doesn't say v of t, because I think that's a little confusing. Velocity times time, okay, or delta t. That's however wide the thing is there. And we know from kinematics that velocity times delta t is simply your change in x, okay, or your change in position if we're doing in all dimensions. So anyway, the area under the curve of a velocity time graph is simply position. I'll write that down too. Area of curve equals, well, it's change in position, which is displacement. So all of these boxes represent some amount of displacement, and when taken as a whole, that makes it the whole displacement between those two times. And when you look at that in integral form, you would say the integral of velocity dt. Oh, I think on my other integrals I forgot the dt. It is always with respect to time. So if we take that integral of velocity with respect to time, we end up with the function for x if we're doing one dimension, or for r if we're looking in all dimensions, if that's general. So our velocity integral ends up being the time. But the same thing happens where you need a constant of integration, okay? Because the area under the curve only finds how far your position changed. It doesn't actually take into account what your initial position was. So our final formula for that is going to be that x, or r if we're doing for general, your position equals the integral of your velocity time function with respect to time plus your initial position. Okay, and I would like to note that initial position is outside of the integral, okay? It is not being integrated. It comes after you've taken that integral. So basically, all you got to do is, if you've got acceleration, you're going to integrate it to get a velocity function, and then you can integrate that to get a position function. And we're going to see here in an example how to use it. So for our example, we're going to be doing example 2.9 from the book, which is motion with changing acceleration. It says Sally is driving along a straight highway at time equals 0 when she is moving at 10 meters per second in the positive x direction. She passes a signpost at x equals 50 meters. Her x acceleration as a function of time is this function, ax equals 2 meters per second squared minus 0.1 meters per second cubed times time. Question A says find her x velocity vx and position x as functions of time. So in order to find velocity and position from acceleration, we're going to have to integrate. So we start with our acceleration function. I'm going to take off units, 2 minus 0.1 t. Okay, that is our acceleration function, changes with time. To find the velocity function, you need to integrate that, equals the integral of 2 minus 0.1 t. So let's go ahead and take that integral. Oh, I forgot the dt. There it is. Let's go ahead and take that integral. The integral of 2 with respect to t is 2t. And the integral of negative 0.1 t is going to be minus. And then you have to raise the power of t. Okay, so t goes from t to the first to t to the second. And then we'll have to divide the 0.1 by 2, so 0.05 t squared is what we get for the velocity function with just the integration. But remember, we have to add on that constant of integration, which is simply the initial velocity. Now, if we go back to the question, we're going to have to find that initial velocity information. So we need to read and see what it says. It says at time equals 0, and that is the velocity, when she is moving at 10 meters per second in the positive x direction. So that's a positive 10 for that v sub 0. So we get 2t minus 0.05 t squared plus 10 is equal to our velocity function in the x direction. Now we've got to take that and we're going to integrate it in order to get our x, or our position function. So for x, we have to do the integral of, I'm going to start with the squared term first. Negative 0.05 t squared plus 2t plus 10. Sorry, I like to have my powers all in order all the time. And we're going to take that integral with respect to time. So the integral of negative 0.05 t squared is going to be negative 0.05 divided by 3 t cubed. And then we got to take the integral of 2t. We'll raise the power by 1. So that is going to be t squared. 2 divided by 2 is 1. So you just have plus t squared. And then for our 10, if it's constant, you just have to tack on the variable. We've got 10t. And that's all great, but we need our constant of integration. And instead of c, we now use the initial value. That is our x naught. And if we look in the question, it says at time equals 0, she passes a signpost at x equals 50. So instead of this x sub 0, I'm going to take that away and make that 50. So this is our position function right there. Now question B asks, when is her x velocity the greatest? So that means we need to find a maximum of this function. And how do you find a maximum in calculus? Well, you take the derivative and you set it equal to 0. Luckily, we actually already have the derivative of this because we know the derivative of velocity is acceleration. Okay? So we need to set 2 minus 0.1 times t equal to 0. So that ends up being 2 equals 0.1 t. Divide both sides by 0.1. You end up with 20. So we get time equals 20 is an extrema of some sort. It's either a maximum or a minimum. In order to figure that out, we actually have to plug the value in, or you could take a second derivative and look at concavity. So really what you should do is plug that in or find a graph of the function and see if it's actually a maximum. It is in fact a maximum, so you get time equals 20 seconds. Okay, so that is where our x velocity is the greatest. And then question C, let's see, I'm going to have to move some of this stuff over. Oh, that moves the whole thing. Never mind. We'll see if we can do question C really small right over here. Question C says, where is the car when it reaches that maximum x velocity? So the easiest way to do this is to take that time is 20 seconds and plug it right in to your, that was a terrible arrow. Plug it right in to your x function. So that would be negative 0.05 divided by 3 times 20 cubed plus 20 squared plus 20 times 10 plus 50, which is a fun thing to type into a calculator. And after you do type it into a calculator, you should end up with 517 meters or thereabouts. All right, guys, that's all there is to integration to connect the position, the velocity, and the acceleration. So to recap everything we know that the position function is r of t. If you want to find velocity of time, you can take the derivative of the position. And if you want to find acceleration, you just take the derivative again, which would also count as the second derivative of your position function. And then in that same vein, we have now learned that you can go backwards. You can do the integral of your acceleration function, tack on the initial velocity, and that will tell you your velocity function. And then you can integrate one more time do the integral of your velocity function plus your initial position to get your position function. Sorry, I keep forgetting the DTs because it's just been a long time since I've actually done calculus. The only slightly tricky thing about any of the integrations is that you always do have to remember those initial values. All right, let me know if you guys have any questions. The practice today is pretty short, so go get rocking and rolling on that. Let me know if you need anything.